Good evening. Hello, my name is Scott Grizzard from the University of South Florida. This is Calculus 1 for fall 2020. Tonight we're going to be talking about related rates. So last time we talked about logarithmic differentiation, and we finished the proof for the product rule, the power rule, both of them. Tonight what we're going to be doing is talking about related rates, which is the kind of physicsy, chemistry, economics kind of applications for all of this stuff. So tonight it's all about applied problem solving. As usual, there is chat in Twitch, which is public. There is chat in Discord, which is private to the class. And our wonderful TA is here today to help answer questions, if you have any. So let's look at what we're doing today. So, oops, wrong camera. So what we want to look at here is we want to look at problems that work like this. So you've got, let's say you're in a bar, as you are, and you've got sangria pouring from a glass. Let's get rid of the rule lines here for a moment. You've got sangria pouring into a glass, and the glass's radius is 1.5 inches. Now, there's motion involved. Things are changing, and that's the big deal with related rates. Related rates are about things that move and change with time, or depth, or price elasticity demand. So things like price, right? Things that change. And that's the whole thing. This whole thing is about things that change. I'm actually going to write that down. This is about things that change. With change. Because if they weren't problems, if they didn't deal with change, of course, we wouldn't be dealing with calculus. Okay? So let's look at one of these problems. And I even have a video for you. Look at this. Right? So I've got sangria pouring into this glass here. And the reason I wanted to do this here was because I wanted to slow down the video. And I thought I had it slowed down. Do that again. So I have this sangria pouring into this glass. And as you can see, the thing moves. The system's changing, right? The liquid is being poured out of the glass, and it's coming into here. And so what I know, I have some things that I know. Sangria is pouring into a cylindrical glass whose radius is 1.5 inches. So I know the radius of the glass, and I know the volume of a cylinder for the formula if I know the radius of the glass and the height. But I'm not interested in the glass itself. I'm actually interested, let me do this. Can I do this? There we go. I'm actually interested in the change in the height. Because if I can find the change in the height, I can then compute the change in the volume. And that's the thing I want to know. I know the change in the height. It's going up at 0.5. It was very difficult to do this. This is a movie we shot last year. And we had to, it took like 6 takes to get this right. And it still wasn't perfect because the rulers is out of thing. But if I watch it, I can actually figure out the change in the height of the sangria. It's a constant rate, right? It's a rate. It's 0.5 inches per second. And that, by using that, I can figure out what the flow is in volume from the tap. And that's what's interesting, okay? So I want to know what the flow is of this tap when I have it like pressed that much in order for the sangria to come out that slowly. All right. So how do we feel 1 to 5 about understanding what this problem is asking you? Okay. It's asking you about a system that's changing. All right. So what I'm going to do, the first thing I'm going to do, although the movie really helped, was I'm going to kind of make a drawing. Right, so what's going on here? There's sangria, there's fluid pouring in. I've got some kind of a cylinder, which is the glass. Right, and I know that the radius of this glass is 1.5 inches. Yeah. So let's write that down. I've got, what's going on here? I've got radius, I'll call that R, and that's 1.5 inches, and that's really fixed. So it's radius R inches, and I'm going to write fixed here because it doesn't move, right? The radius of this glass, or the radius of the sangria in the glass, which is actually what I'm interested in, doesn't change, right? The glass fills, the radius is still the same. I mean, yes, there was a bottom at the top of the glass, but I'm not counting that. I'm not looking at like a cone. If I was filling up a cone, the radius of the water in the cone would change as I filled it up. But here I'm not. Here I'm just filling a cylinder. Okay. Now, I have some height, right? There's the word height. Radius, I've got height. And I don't know what the height is. But the height is moving. So the height of this fluid here, which is what I'm really interested in, this very lightly purple colored sangria, which I probably wouldn't drink because it looks a weird color, is going up. So there's motion here associated with the sangria. Okay, and I've drawn an arrow there. I want to know that it's moving. And it's got some flow, and it's got a second there, right? So you see this increasing at a rate of per second. Okay, that's time. So I've got time going on here. Height should be h. Time is t, and that's in seconds here. All right. And that changes. But it does more than change. And I'll get to what I mean by it does more than change in just a second. Now, volume is another thing that's changed. So I got volume, V. And I don't have a unit associated with it, but I see inches here, inches here. That means I'm going to get cubic inches. And the volume changes. So we'll call that a moving. Then I've got rate of height changing. And rate of volume. So the rate of height is dH. Now, it changes in terms of seconds. So that means time is not only moving, it's driving. It's the thing by which I'm going to take a derivative. Height should be h here. So this thing is not only moving, this drives. So I'm going to put the variable that drives on the bottom here. I want to distinguish these variables here from these variables here. So this is dv dt. And both of these, so this is in inches per second. And this is in volume per, this is in cubic inches per second. All right. And these variables are kind of special here. So I kind of want to, they're not really moving. These are the things that are moving with time. All right. So I just kind of want to, I don't need to put like drive fixed or moving. So this is kind of what's going on. Now, I also have a relationship to these things, and that's the volume of a cylinder. So the relationship. The volume of a cylinder is the circle on the top right? So if I take the area of the top and I multiply it by the height of a cylinder, I get the volume. So the volume of the cylinder equals pi r squared times h. Okay. How do we feel about that, 1 to 5? And inevitably, I get the question, well, do we have to know all these formulas for the test? If you look at the study guide, if you look at the study guide, it'll tell you what formulas you need to know. You need to know area of a circle. You need to know the simple things. Area of a circle, area of a square or rectangle, perimeter of such things. You need to know you don't need to know the volume of a sphere, but you need to know the volume of a cylinder, the volume of a rectangular prism, otherwise known as a box. And the list is on there, right? We expect you to know the Pythagorean theorem. All right. We don't expect you to have the volume of a hypersphere, hypervolume of a hypersphere at your beck and call, or the volume of a cylinder, or the volume of something like a pyramid or a tetrahedron or whatever. Okay. So if it's more complicated than the volume of a cylinder, we will give it to you. But the area of a circle, you get to know. Okay, anyway. Volume equals pi r squared times h. So what I'm going to do now, since r is fixed, it can go in now. And that's important. R here is fixed. So what I'm going to do is I'm going to put R in right now. So that's V equals pi times R, which is 1.5. Squared times H. Okay. Now I'm going to take the derivative with respect to time. And it's usually time, but it doesn't have to be time. Okay? So what I'm going to get is I'm going to get d over dt of the left equals d over dt of the right. Okay? So people are having lag issues. Try refreshing OBS. Not OBS. Twitch. Sometimes that fixes it. And what it winds up happening is here I get dv over dt. Now, these are constants. So they'll come right out. And I wind up with pi times 1.5 squared. I should probably do that, right? Times dh over dt. How do we feel about that little derivative 1 to 5? Okay. Let's go ahead and put 2.25 in here, by the way. Let's just do this. All right. Well, notice now I have a relationship between the change in volume and the change in height. Okay. Now sub in the data. Okay. So my moving data was 0.5 per second. So I'm going to get dv over dt equals pi times 2.25. That's a decimal there, by the way. And we'll go ahead and put 3.14 in there. Makes it an approximate. Times 2.25 times 0.5. And the only reason I'm putting in a decimal for this is because I had decimals in the answer. If I didn't have decimals, I'd want to leave everything like it was. Okay, so I'd want pi in the answer if I didn't have that. Now the units on here, this was a squared, so this is inches squared. And this right here is inches per minute. So when I get my answer, it should come out to be the correct. Okay. So I'm going to wind up with 3.14 times 2.25 times 0.5. And I wind up with something like 3.5325 inches cubed. And this was per second or per minute? Per second. Okay. And then what I'm going to do is I'm going to do a little statement. I'm going to say the following. So, the sangria is pouring from the tap at about 3.5, that's good enough, cubic inches per second. Okay, so how do we feel about that problem 1 to 5? And that's what we mean by a related rate, right? There's two things happening here. I'm sorry, there's things being driven, right? There's a rate that the height is changing, and that influences or allows you to solve the rate at which the volume is changing. And that's kind of important for these problems. So let's go back over these steps here that I have here for solving these problems. So let's look at what I did. There we go. It's like way too zoomed out to be any good, right? Let's put the steps over here, and then when I do the paper version, I'll move the steps back to where they're in line. Okay, so let's look at what happened here. The first thing I did was draw a picture. Do that first. Always do that first. Second thing I did was I looked at these variables and I figured out what's moving and what's not. And, you know, for a simple problem like this, I may not have done everything, but the important thing here is that R is fixed and H is moving and V is moving and T is driving. Right? These are the things that change. Right? And I kind of, you know, I gave myself the units here because the units are a good hint, and that's a good thing to say. The units So the fact that I had this unit here, inches per second and cubic inches per second, this inches per second, that per second thing really gave me a hint that time was the thing going on here. Now, I sub in the static stuff first, but only the static stuff. And we'll get to what the difference is in just a moment to be sure here. So the radius was fixed, right? It never moved, so it went here. Now, if this had been a problem with something like a cone, the radius would have been changing as the height of the water increased. And in which case, I would have had to find something out, a different relationship that was fixed. But if it had been like the radius of if I had been doing a cone, as the conic cup filled up, the radius would get bigger. So it wouldn't be fixed, it'd be moving. But in a cylinder, the radius, no matter what the height of the water is, the radius is always fixed. Okay. Now I implicitly differentiated in terms of the thing that drove, in this case, time. And then I would substitute any snapshot data. We'll get to what that is in a minute, but this is where I sub in the moving stuff. So I didn't have a V or an H left over, right? They went away, and all I was left with was a dV over dt and a dH over dt. So then I subbed in the 0.05, and because I was dealing with decimals, I went ahead and changed the pi to 3.14. Now, if I wasn't dealing with decimals, I wouldn't have done that. I would have kept it like it is. And then I checked to make sure my units made sense, right? Here's inches squared, right? So the radius here is in inches. That means the area of the top, which was pi r squared, is in inches squared. And this unit's in inches per minute. So when I multiply over my units, I should get inches cubed per minute, which is exactly what I get. Or I'm sorry, inches per second. And so I saw my number, and then look what I did here. I checked that my units made sense, and then I actually wrote what I meant by this. So I said the sangria is pouring from the top at about 3.5 cubic inches per second. And the reason why I write that is because I want to say exactly what I mean. I don't want the grader or the reader to interpret the sign on my units, on my answer. So there's sometimes when the question asks you, what is the rate? Is it increasing? When the thing is actually decreasing and it wants a negative. But if I say, at least on a test, now WebAssign, of course, doesn't have a grader looking at it. But if a grader's looking at it and you tell the grader what you mean, the rate is decreasing at a rate of 25 centimeters per second, right? And the question asks, oh, what rate is it increasing? So the answer should have been negative 25. The fact that you said it was decreasing at that rate means that you win. You get to control the direction of the units. And that's important. So there's no ambiguity. Well, what did you mean, up or down? I told you what I meant. Okay. So let's bring these steps down here and look at another problem. And I got two problems. They're starting to stack up together. Hold on. That was example number 3. I'm going to use that baseball diamond later. So let's look at another problem. If you're a scuba diver, are there any questions, by the way, about this? I don't see any. Can I explain how I got the units for dVdt? Did I do that to your satisfaction? The fact that what I did was I took the, I had inches squared because this was the area. Right, so the radius was in inches and then I squared it, so I got inches squared. And this is inches, so I got inches squared times inches per second, which equals inches cubed per second. So it makes sense. Okay, perfect. All right. Let's look at a new problem. In the ocean, pressure, we're going to measure it in bar instead of PSI or kilopascals or whatever else you want to measure it in. We're going to measure it in bar, which is basically an atmosphere. Okay, a bar is about 1 atmosphere. One atmosphere absolute, which is different than ATM, maybe. Right? There's a difference between don't get me started. There's a difference between gauge and absolute pressure. Okay, so as I descend, okay, for every 10 meters I descend, the pressure increases by 1 atmosphere. Okay, so here I am at the surface. And at the surface, otherwise known as a depth of 0 feet, right? The pressure is 1 atmosphere. So at 0 feet or 0 meters, it's 1 ATA, or otherwise known as 1 bar. This is, you know, approximate. Now I go below the surface. I go to 33 feet or 10 meters. And my new pressure is 2 ATA or 2 bar. And I go down a little deeper. If I go to 66 feet, which is 20 meters, I get to 3 ATA / 3 bar. And at 99 feet, which is about 30 meters, this is, by the way, in salt water. The freshwater, it's a little bit different because freshwater is less dense. Specific gravity is lower. And so on and so forth. So I go down here to 40 meters and I get 5 bar. And I go down to 50 meters and I get to 6 ATA. So how do we feel about that? As I go down, pressure increases, right? Should be 165. There we go. Little scrambled now. So pressure increases as I descend. By the way, the limit for recreational scuba diving is, well, it's right above this. That is technical diving, is everything down here. And this is kind of initial training, is the 99. Well, depends on the agency. 66 or 60 into your patty. Any questions about that? Okay. So this is all, and why is this important? Well, there's something called Boyle's law. And Boyle's law is PV, pressure times volume is a constant. And Boyle's law is very important if you are a scuba diver. Does anyone know why? Why is Boyle's law? So someone's posting the entire thing in there. I don't care about the rest of it. The bends. The bends are a partial pressure thing. That's really Dalton's law. It's a good guess, though. There's something even more important with Boyle's law. Boyle's law is important because if your lungs are filled with air, correct? And if you're not careful, let's see, do I have the, no, I don't. I used to have a very cool little demo thing, but I don't have it right now. So if your lungs are filled with air and you hold your breath at 99 feet and you suddenly go up, the volume is going to expand 4 times. So if your lungs are filled with air, you're going to go, eat, boom. Your lungs will explode when you get to the surface. It's not a very pleasant thing to happen. Okay. So that's Boyle's law. Boyle's law states that the volume in liters of a sample of gas under pressure satisfies this equation. All right? If you're down at 100 feet, you hold your breath, come to the surface, your lungs explode. Now, assuming that temperature is constant, and suppose a deep diver, Diver Dave, exhales a bubble of air, which rises to the surface. So the question is, when it reaches 40, he's a trained technical diver, by the way, because since he's diving deeper than 40 meters. Now, as the bubble goes up, it's going to get bigger, right? Is everyone on board with that? Because as the pressure decreases, the volume is going to increase. Right? So volume increases. As pressure decreases. So what's going to happen? So the question is, at 40 meters, what's the rate at which the bubble is changing? Okay. So note that this doesn't have, so let's look at the variables here. All right. I've got depth. That's in meters. I've got pressure. And that's in bar. I've got some C, that's a constant. Depth, I'm going to call this D, even though I'm going to hate myself for it later. I'm going to call that P. I've got a constant, gas constant, don't care. And this is going to change. This changes. This is fixed. And I've got volume. And that's going to be in liters. We'll call it V, and that changes. Now, what is changing here What is the rate of the volume changing with respect to depth? Ah, depth is the thing that's driving. How do we feel about that, 1 to 5? So here's my picture. I expect the volume to get bigger as the air pressure decreases. And my question is, what is the rate the volume of the bubble is changing? So I'm going to have dV over dd. I'm also going to have dP over dd. I'm going to have the change in volume. I'm going to have a change in pressure. All right, so pressure is going to change with depth and volume is going to change with depth. And I've got this thing that relates them here, which is PV equals C. So I'm going to take PV equals C, and I'm going to take the derivative of both sides with respect to depth. Now, note, there's nothing fixed for me to sub in except the constant. Or 1 liter of volume. Or the 5 bar. Okay, all of those things move. Okay, so those are all things that are changing with respect to depth. So I can't sub them in yet. That's big. Okay, the only thing that's fixed is the constant C. Okay. So what am I going to get? I'm going to get these. So here I'm going to need a product rule because these things both move. So I'm going to get the derivative of the first, d over dd of P times V plus P times d over dd of V. And that is going to equal the derivative with respect to d of C, but C is constant. That makes our lives a little better. Okay. So now what do I do? Well, I've got to have dP over dd times V plus P times dV over dd equals 0. Now sub in the data. So let me say what I mean about the snapshot here. There are things that are moving, and there are things that are fixed. Now, the things that are fixed in time. They don't change. Time, depth, whatever. The things that don't move, period. Okay? And then there's a moment in time or a moment at depth where I have the snapshot, where I've taken a picture of things that are moving. Okay? And that's this data. So let's make a note here. Right? Because D, P, and V change in the problem. D equals, what was it, 40? 40 meters. P equals 5 bar. And V equals 1 liter is snapshot data. Right? Is everyone on board? 1 to 5, how do you feel about this? That the thing's moving and then suddenly I freeze it and I take a snapshot. But snapshot data is still moving things. I can't, when I take my derivative, I'm taking the derivative of everything that moves. Then I put in my snapshot data. That's different than up here. Here, R is fixed forever. Right? It doesn't change during the thing. It's not a moving thing. It's fixed forever. It's always 1.5 inches. So there's a difference between things that are fixed and things that are snapshotted. Okay. So now I put in the snapshot data. All right, the snapshot data is this. I got dV over dP. I don't know. I know what dV over d. I don't know. This one's a want. Okay, this one I have. Oops, wrong color. So I've got to have dP over dd. Now, at my snapshot, the volume was 1 plus the pressure. I should say this is 1 liter. Plus the pressure at 40 meters of depth, which is 5 bar, times the change in volume, which is corrected. So this is bar, times the change in volume with respect to depth, which is not volume. I'm sorry, the pressure with respect to depth. So, sorry, this is the thing I want. My bad. Right? dP over dd I have. That's 1 over 10 meters. I'm sorry, bar per meter. This is the thing I want. dV over dd. And that all equals 0. Okay. So what I'm going to do is I'm going to do a little mathy here. I'm going to move this over to, I'm going to move all of this over to the other side. And I wind up with 5, which is bar. dV over dd equals, this becomes a negative 1 over 10. And this is a liter bar per meter. And I'm going to divide both sides by the 5 bar. And I wind up with dV over dd equals negative 1 over 10 times 5 liter bar over meter bar. The bars will cancel, and I will get my liter per meter of depth right here. So I wind up with -1 over 50 liters I don't know why this won't write today. With an apostrophe, right. Liters per meter. Now, I've got a -1 over 50. What I'm going to do is I'm going to say what I mean. And I'm going to say what I mean. The depth is decreasing. The bubble's going up. So as the bubble rises, the volume is increasing at a rate of 1 over 50. Or I would say that the volume decreases by a rate of 1 liter for every 50 meters as the volume when the bubble is at 50 feet. So I could say either one. I could say it's increasing at a negative rate. I'm sorry. Oh, that was part of the data that was given to me. So someone's asking at what rate. This is it right here. 1 over 10 bar per meter. Okay. So I'll just write that here, that dP over dd equaled 1 over 10 bar per meter. Okay. Well, the 40 meters do matter in that the 40 meters is the thing that makes it 5 bar. But no, the 40 meters is superfluous data that you don't have to put in anywhere. So that's another thing these problems can have is traps, right? They can have irrelevant snapshot data. I didn't need it. But look at what I did here. I drew a picture first. I identified the variables. I identified what moved, what stood still, and what drove. I identified the relationships. I substituted the static, non-moving, and only non-moving things. Then I differentiated implicitly. Then I substituted in my snapshot data. Not before, then. Solve, check that my units made sense, and I said what I meant. 1 to 5, how do we feel about this problem? I know I took a long time to do it. Okay. Let's look at another one. Baseball seems a little appropriate. Someone cue up, the song about Katie Casey. Oops. We have an error. Okay, well. Let's move you down here. It's going to like pop up with a conflict in just a minute. Okay. So a baseball diamond is a square with 90-foot size, right? It's 90 feet from home to first, 90 feet from first to second, 90 feet from second to third, 90 feet from third to home. Okay? Now, the runner on first is going to try to steal second. So the minute that the baseball pitcher starts his motion, right, toward the home plate, the runner on first is going to take off for second. Right? So now as the pitch heads home, how fast now the runner is taking off at a certain speed. Right? That's what this is saying. As the pitcher begins his motion, the runner makes a fast dash. The runner on first makes a dash for second base at a speed of 24 feet per second. Right? So the runner is doing this. The base stealing runner is halfway there when the ball hits the catcher's mitt. At what rate is the runner's distance from home plate increasing? Okay, so we know the rate at which the runner's distance from first base is increasing, but we don't know. We want to know what this rate, what the change is here, because the throw to throw him out is going to come from home. So it's the relative velocity. It's that velocity that really matters, not the speed of the runner, so to speak. Or at least that's one way to think about it. Not really, but you get the idea. What do you want? It's a math problem, right? So we have this kind of triangle thing going, right? I've got the runner's distance from first to second, the runner's distance from home, the distance from home to the runner, and this edge here. Well, it looks like a right triangle to me. I'm going to give me some labels. Okay, so we've got so what's going on here? We've got the distance from runner to first. We have the distance from runner to home. Now, I've got two triangles I can work here. I could work with this triangle, but that's not, I'm going to have to do law of cosines or something like that to get a handle on that. But this triangle, that one looks nice. That's a right angle right there, right? It's a square. I think we'll go with that one. Does anyone object to me choosing that triangle to play with on the distances instead of the other one? So I've got a distance from home to first. Okay. Now, I've got some snapshot data. And I've got some fixed data. So let's look at what's going on here. I'm going to call the distance from the runner to first base, I'm going to call this side A, just, because. And I'm going to call this side B, and to be very original, I'm going to call this side C. Right, so the distance from the runner to first, that's A. This is B. I'm sorry, that's C. The distance from home to first is B, and the distance from the runner to home is C. Now, this moves. This moves. This is fixed. And it's not fixed as in a snapshot. That's fixed. And the thing that's happening here is feet per second. That means time's involved. All right, what's the relationship here? Well, the relationship is a squared plus b squared equals c squared. Right? And I'm going to write here that this is 90 feet. Now, my snapshot data, let's just write that down for the moment. All right, so I know that d a over dt equals 24 feet per second. Should put some units here. This one is feet, 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 seconds. I know that the pitcher, the base stealing runner is halfway. So in my snapshot, A is going to be 45 feet. And that's what I have. So that's my snapshot. But since A moves, I'm not going to sub in A yet. And now I have my relationship. Well, my relationship is A squared plus B squared equals C squared. Since B is fixed for all time, forever and ever, the distance from home to first is 90 feet. That does not change. I sub it in now. So I'm going to have A squared plus 90 squared. I'm going to leave that as 90 squared. I'll show you why in a minute. Equals C squared. So now I take the derivative with both sides with respect to t, and I get d over dt of A squared plus 90 squared equals d over dt of C squared. Chain rule. Well, sum rule, this is a beautiful thing. This is a constant. See why I didn't bother with the 90 squared? This is a constant. And it's a constant alone. It's not being multiplied together by anyone. Right? Up here, I had a constant that was being multiplied. Which one is it? Here. So this one was a constant multiplied, so it came out. Right? It was multiplied by something that moved. But here, I've got a constant, and it's just on by its lonesome. Right? It's being added. It's by itself. It's lonely. And because it's lonely, we're going to kill it. It dies. It goes to 0. So what I have here is d over dt. I'm going to need a chain. Let me just go ahead and pull this sum out real fast. I'll do it at a second step. Hold on. Go back. There we go. I spent like way too long doing this, right? It would have taken me much less time just to rewrite it. Much less time. We'll do the sum rule. All right, so what I'm going to do is I'm going to take the derivative of this with respect to t. I'm going to need a chain rule. So this is going to be d over dA of A squared times dA over dt plus 0 equals d over dc of C squared times dc over dt. This here becomes 2a dA over dt plus 0 equals 2c times dc over dt. I'm going to divide out the 2's and get rid of those. And now I have my relationship. Now I need my snapshot data. I don't have C. So I need to solve for it, okay? So I've got a squared plus b squared equals c squared. In my snapshot, that's 45 squared plus b is 90 squared equals c squared. Now, the previous problem actually did need the chain rule. So in the previous problem, I did do the chain rule. I did it right here, right? Because I didn't know what the derivative with respect to p is 1. The derivative with respect to p to itself is just 1. Whereas here, so I did use the chain rule. There just wasn't anything to chain, right? It was a 1. It went bye-bye. Whereas here, I've got an outside. I've got something being squared. Okay? And because I have something being squared, I kind of had to deal with the squaring of it. It's a good question. It's not a bad question. Okay, so now here I'm going to do a little voodoo. I mean, I'm going to do some serious math foo right here. I'm not even going to plug this into my calculator. Of course, I'm going to mess it up, right? But let's see. This right here, 45 squared is 45 times 45. Plus, now this is 2 times 45 times 2 times 45, right? 90 times 90 is 2 times 45. So what I'm going to do is I'm going to factor out all the 45s. And I'm going to get 45 times 45, 1 plus 2 times 2. So this becomes 45 squared times 5. So this right here, I take the square root of both sides and I wind up with 45 times the square root of 5 equals c. Voodoo. Math voodoo. The reason that works is because this is 45 times 2. So I'm about to square 45 times 2. What I'm going to do is I'm just going to pull everything out with the distributive property. And when I square root that 45, it's going to become 45 squared. It becomes a single 45. And I'm just left with the square root of 5. Okay, so now I have c. So now I'm going to have a. A is 45 feet. dA over dt is 24. Equals 45 square root 5 feet times dc over dt. And dc over dt is what I want, so I'm going to divide both sides by 45 times the square root of 5, and I get 45 times 24 over 45 root 5, and my units become feet, feet over second over feet, and that's going to equal dc over dt, which will become feet per second, which is what I want. Goodbye. So the distance from the plate to the runner is increasing at a rate of 24 over root 5 feet per second. And I'm done. How do we feel about that 1 to 5? Right? Now, granted, this right here is math voodoo. Okay, the way that I solve for the square root of 5 thing. That's, that 45 root 5 thing. Most people would put that into a calculator, and that's kind of, you have to be kind of aware of those things in order to pull that one off. But these other pieces, right? I mean, 24 over root 5, I would have wound up with some decimal. How do we feel about this 1 to 5? Okay. All right. So there's one last thing I want to talk about. But remember this thing. Remember just these steps. Okay? Here are the steps. Where did I put the steps? Where'd the steps go? The steps get moved? Yeah, here they are. Draw yourself a picture. Figure out visually what is going on. That's important. You have to figure out visually what's going on. As a matter of fact, I'm going to put that here. Draw a picture. Figure out visually what is moving and what is fixed. And I cannot stress that enough. Drawing the picture is probably one of the 2 keys to the problem. Okay? It's this one. These are the important key points. That, draw a picture to figure out what's moving. And the other one is, don't sub in snapshot data until after the derivative. If there's that's the 2 big points to take away from this. All right? Figure out visually what moves and what doesn't. Draw a picture. And don't sub in snapshot data till after. There's a difference between the whole moving picture and me hitting the pause button. Okay? There's things that are fixed over the length of the movie, and there's things that are fixed when I hit the pause button. And those are 2 different types of things. Okay? That are only fixed when I hit the pause button. 1 to 5, how do we feel about that? There are things that are fixed for the entire movie, and there are things that are fixed when I only when I press the pause. That's big. I cannot stress enough to think, see, I got a picture here, I got lots of pictures here, I figured out what was going on, I got pictures here, right? I got pictures here. Heck, this one even came with a movie. I drew pictures of everything. All right, we have one last thing for tonight, and that's the formula for the linearization. All right, so this is a definition. We should say that this is completely different. Okay, we've got a definition. I want this in purple. So let f be a function differentiable at x equals a. Okay? I need the grid back because now I'm going to just be all over the place. Yeah, see? So I'm all rosed here. This is horrible. All right. The linearization of f at x equals a is the function LFA of x equals f of a plus f prime of a times x minus a. Okay, so these are parameters. The book does this. If you want to know book version, L of x equals f of a. So it's the same thing, just the book doesn't have those two parameters on it. If you'd want to do it without the parameters, I'm okay with it. But I encourage the parameters. So these are the parameters. The reason why you want to do that is because sometimes you want to have a bunch of a's on there. So if I have like the linearization of x cubed, I might have it at -1, at 0, and at 1. And I might want to be comparing the linearizations. So I like to draw it with the parameters. Some people don't. Some people just have the a parameter. If you know what you're talking about, if you know what f you're talking about, it's perfectly fine to leave off the f parameter. If you know what a you're always talking about, it's perfectly okay to leave a, you have to communicate which one of these functions you're talking about. So the linearization function for f at x equals a, in some books, not ours, gets denoted LFA because they want to be specific about where it is, of x, right? But it's a function of x. 1 to 5, how do we feel about that? And that will be, so we're going to talk about the linearization next time. So next time, we will do linearizations and Taylor polynomials and differentials. And that will be the conclusion. This stuff is the conclusion of test 2. Taylor polynomials never make it on the test, and differentials almost never do. But I'm going to include Taylor polynomials because this sets up something for Calc 2. It's going to be briefly. And if you've never, if this is the terminal course, if you're going to med school, you're going to want the second order Taylor polynomial kind of in your pocket, because you'll see it again in a couple formulas. So it's one of those things that the book doesn't cover till way later, but the life science book covers now. And I just want to make sure that you've seen it if you're going to med school. I'm going to spend like 10 minutes on it, maybe 15. And then we'll talk about differentials. But the big thing for next time is linearizations. Are there any more questions? So today we talked about related rates. Don't forget that Sunday there is at 7 p.m. on Sunday will be the first test review. There's no test review this time on Wednesday because I'm doing Sunday, and then I'm going to do one on Thursday, and then I'm going to do another one on Friday that actually goes over the bootleg. I'm going to have parts of the bootleg up probably tomorrow, but the full bootleg up when I get the rest of it approved. And she said that she'd have it done by tomorrow night. So hopefully as soon as I get that, I'll do it. Next week, we're going to be doing related rates problems during the class, the regular class time, not during lecture, but the regular class time. The activity packet is just a bunch of related rates problems, all with like different little scenarios that you can see. Because I want to get you, there's usually like a 12-pointer on the test. So next week, the problem set is going to be nothing but related rates problems. And we will do linearization, and you'll have a quiz on linearization. And then next Tuesday, lecture is the cutoff for the test. So, I'm sorry, not Tuesday, Monday. So Monday evening's lecture, or I should say Wednesday's quiz, which is on Monday evening's lecture, is the cutoff for the test. Any questions? Any other questions? Comments, issues, suggestions, thoughts, hate mail? Okay, well, that's it for me for tonight then. Have a good one. And don't forget the steps here. And please remember the difference between the snapshot data, the whole movie, what moves during the movie, and what is fixed for the whole movie and what's fixed only when I hit pause. Okay,